The VDB analysis sub is a very powerful tool that not only allows us to calculate a gradient from an SDF, but also an SDF's curvature. But before we put that to use, let's talk about what is curvature. Well, think about this. You have a slice through your geometry, which is this kind of weird looking curve. And you'd like to know how bent a point or a voxel at a given point is. So for example, how bent is this point here? How bent is the surface on this point here? So what we do is we draw this point's normal or this point's gradient, which we can derive. And along this gradient or this normal, we are looking for a circle that has a radius, so it kind of kisses this curve as closely as possible. That means we're trying to find a circle which fits as closely as possible on that curve going through this point. And this is called the osculating circle. So curvature in our case in Houdini in the VDB analysis sub is defined as 1 over this circle's radius. So 1 over osculating circle's radius, 1 over r. But what happens at this point, for example? I mean, if we drew a circle in here, this could be infinitely big. If we happen to be on the outside of our geometry, we just draw the circle in the other direction and change the sign of the resulting calculation. So in this case, our curvature would be negative. Or to put it differently, a convex curvature is positive and a concave curvature is negative. So let's just quickly have a look at how this works in Houdini. And what I did is I dropped down a platonic solid here, set this to icosahedron, then converted it to a VDB, dialed down the voxel size to 0.02, and on the one hand directly converted this back into polygons, and on the other hand dropped down a VDB analysis sub and set this to calculate the curvature. Then I dropped down an attribute from volume sub, and what I did in here, I transferred this curvature attribute onto the polygons that we just generated, and within the sub I just set it up to transfer only one component, because the curvature is just a one-dimensional value, a scalar, so there is no need to transfer 3 components as you do for a vector. And also I gave the attribute the name curve. So when I go into the geometry spreadsheet here, I can see my curve attribute here ranging from minus 0.15 to 63 point something. And this can arbitrarily change depending on the geometry that you put in there. For example, when we go back to our platonic here and exchange the icosahedron for a tetrahedron and go back down here, we can see my curvature now goes from 133 to minus 3 point something. So you still have those previous slides in mind, and you're thinking a negative value. That means this object must be concave somewhere, but when I look at this, this is not concave. So let's try visualizing what's going on. And I drop down this visualize node, and let's set it up to visualize the curve attribute, and the min and max is still set to the values of the icosahedron. So let's exchange that, and we're going from minus 3, let's say 3.7 to 100, let's say 134. Let's highlight this up, go to a scene view. And we can clearly see, yes, this is correct. The curvature here, of course, should be very high, and it should be even higher at these very steep polygons here. However, where are these negative values? And in order to visualize, let's just clamp the maximum down to 0. And we see those values appearing here. And till this very day, I'm not sure where they stem from. And I have this suspicion that they are just arithmetic errors from the implementation, or maybe precision errors. But in general, compared to the proper value of our curvature that we have, in most cases they are negligible. Okay, so now you've seen that calculating the curvature actually works. Let's put it to use.